Yeah. Very good afternoon to all of you. It gives me immense pleasure while welcoming our head of the department, Dr. Rupaban Subedar sir, external examiner, Professor S.J. Bhosle sir from VJTI Mumbai, my colleagues from Department of Electronics and Communication Engineering, Dr. Juesh Pinong, Dr. Jaideep, Dr. S.K. Datta, and few of member from VJTI, Professor Bhosle sir students and their research fellow researchers, and member from Lightwave Communication System, as well as Dr. Dhiman, who happened to be my ex-student now, and and uh, and dear researchers and friends. In this PhD Viva seminar, Mr. Himanshu Ranjan Das is going to give his presentation on design of directional coupler based silicon optical modulator. Before inviting him, I would like to welcome again our external examiner, Professor S.J. Bhosle sir, who is presently head of the Department of Electrical Engineering in a very famous and very old institute, that is VJTI, which was 133 years before Britishers have established, and it is serving to the country at great extent. So, with your permission, sir, Professor Bhosle sir, can I invite Mr. Himanshu Ranjan Das to proceed further for his presentation?
Yes, sir, definitely. Himanshu present it coolly. So anyway, once you finish presentation, we'll ask you the questions and be ready.
Yeah.
All the best.
Okay, sir. Thank you, sir.
Thank you so much, sir. Yeah, now Himanshu, you can present, and later on we will have a question answer session. Thank you. Yeah, over to you, Himanshu.
Okay, thank you, sir. So first of all, a very good afternoon to all of you. My name is Himanshu Ranjan Das. So today I'll be giving my Ph.D. Viva Voce seminar on the topic Design of Directional Coupler-based Silicon Optical Modulator under the guidance of Dr. Subhash Arya, sir. So these are the outlines of my presentation. So first of all, I'll go through the introduction, then a brief literature review, then the motivation and challenges. After that, I will come to the problem formulation and scope of research, then the objectives of the thesis. After that, I will come to the contributory chapters in the thesis. So in this thesis, we have 3 contributory chapters. The first one is the architectural design of silicon-based optical modulators. The second one is the comparative analysis of VO2, that is vanadium dioxide, and ITO, indium oxide-based electro-absorption modulator. And the third chapter is a V-shaped ITO-based electro-absorption modulator. After that, we'll go through the conclusions, then the limitations and future scope of the present work, then the publications as the outcomes of the thesis, then references and acknowledgement. So coming to the introductory slide. So here in figure 1a, we can see that it shows the silicon photonic market forecast by application. So here, the silicon photonic market was estimated to be around $480 million in 2019, and it is expected to increase up to $3.9 billion by the year 2025. So in overall compound annual growth rate of 40% is expected by the year 2025. So here, most of the industries is occupied by the data center transceiver, which is having a market of $3.6 billion, and the next is $186 million, which is occupied by the long haul transceiver, and so on. So from here we can see that designing of silicon based optical modulator is a market driven research to address the issues of fast modulation speed, less power consumption, and comparable package density with VLSI electronics. Now coming to figure 1b, it shows the silicon based optical modulator. So here it shows the cross-sectional view of a silicon-based optical modulator, where this green color indicates the plasmonic material, this black color indicates the dielectric material, which is sandwiched in an SI waveguide, which is indicated by this orange color, that is silicon waveguide. And below we can see the on-state and off-state of the device. So this working principle and this device structure, I'll be going to explain in the coming slides. Now coming to literature review on plasmonic material-based modulator. So serial number 1, we can see Vijay Sorgi et al. So these authors have designed an ultra-compact silicon nanophotonic modulator which is having a thickness of 10 nanometer of ITO, which is a plasmonic material. And the structural design consists of a silicon, indium tin oxide, silicon dioxide, and gold, which is stacked upon a silicon substrate. And in doing so, they have achieved an extinction ratio, insertion loss, figure of merit, and energy consumption per bit of 1 dB per micrometer, 0.04 dB per micrometer, 25, and 28 femtojoule per bit, respectively. So this work was published in the year 2012, and this work has been cited by around 389 papers. Now, coming to the next author, A.P. Vasudeva et al. So these authors have designed and demonstrated an electro-absorption modulator where they have kept the plasmonic layer above the SI waveguide. So their plasmonic layer, that is the indium tin oxide, was having a thickness of 10 nanometer. So in doing so, they have achieved an extinction ratio ER of 0.11 dB per micrometer and FOM of 36.67. So this work was published in the year 2013 and it was cited by around 158 papers. Now coming to serial number 3, A. Josonghani et al. So here the authors have utilized the plasmonic material vanadium dioxide. So in doing so, they have observed the performance, and their performance was IL equals to 0.86 dB per micrometer, ER equals to 2.3 dB per micrometer, and FOM equals to 2.67 respectively. And this work was published in the year 2013, and it was cited by around 108 papers. Now coming to serial number 4, H.W. Lee et al. So here the authors have experimentally demonstrated an ultra-compact plasmostar. So a plasmon slot waveguide field effect modulator based on transparent conducting oxide active region. So by electrically modulating the conducting oxide material deposited in the waveguide gap, so they have achieved a high dynamic range of around 2.71 dB per micrometer with low waveguide loss, which was around 0.45 dB per micrometer. So this work was published in the year 2014 and it was cited by around 257 papers. Now coming to the next slide, here Adju et al. So the authors here have designed an ultra-compact electro-absorption modulator, and their structure comprises of titanium nitrate, hafnium dioxide, indium tin oxide, and copper material. So the design modulator showed an ER-IL FOM and EBIT of 3.95 dB per micrometer, 0.88 dB per micrometer, 4.48, and 400 femtojoule per bit, respectively. And this work was published in the year 2014, and it was cited by around 52 papers. Now here, another authors, Shillong and A.S. Hamle. So here they have investigated a dynamically reconfigurable nanoscale modulator where they have utilized bilayer indium tin oxide. So in doing so, they have achieved an extinction ratio of 4.83 dB per micrometer, IL of 0.03 dB per micrometer, and FOM of 161. And this work was published in the year 2015, and it was cited by 48 papers. Now next, P. Markov et al. Here the authors have presented a computational design for the integrated electro-optic modulator. So here they have used vanadium dioxide as the plasmonic material. Here they have observed an increase in the extinction ratio per unit light, which was around 9 dB per micrometer compared to other photonic and plasmonic modulator. And this work was published in the year 2015 and it was cited by around 50 papers. Now coming to serial number 8, M.K. Shah. Here M.K. Shah have demonstrated a new architectural design for the plasmonic based modulator. Here they have inclined the lower part of the SI waveguide at a particular angle of 84.09 degree. In doing so, they have achieved an enhanced performance matrices at a communication wavelength of 1550 nanometer, and their work was published in the year 2018 and it is cited by around 5 papers. Now the last M.S. Taharsima et al. So here they have experimentally demonstrated a novel coupling enhanced dual gate ITO modulator, and they have observed their performance in terms of ER, which was around 0.5 dB per micrometer, and IL, which was around 0.5 dB per micrometer. Therefore FOM is equals to 1 respectively, and this work was published in the year 2019 and it is cited by around 13 papers. Coming to the motivation and challenges, so here in figure 2, here we see the operating speed versus the critical dimensions. So in the past, we were not able to achieve higher operating speed as well as not able to fabricate devices at lower dimensions. So if we go for electronics, then with the help of electronics, one can achieve lower dimensions, but it was not able to achieve higher operating speeds because electronics is limited by the RC delay. And if we go for photonics, we can achieve higher operating speed. But since photonics is diffraction limited in size, therefore we can achieve lower dimensions with the help of photonic components. Therefore, we go for plasmonics. So if you go for plasmonics, we can achieve higher operating speed at lower critical dimensions. But in doing so, there are some challenges because integration of plasmonic, electronic, and photonic component together is a challenge. And since we are going to incorporate plasmonic material in the device, so structural optimization is required for the device. And since the device we are going to design is miniaturized in size, therefore fabrication of such kind of devices is a challenge. Now coming to the next slide, these are the problem formulation and scope of research. So here, developing a miniaturized silicon optical modulator for photonic integrated circuits. The next one is the optical characterization of plasmonic material used to design the structure of silicon optical modulator. The next one is designing the architecture of silicon optical modulator and incorporate the plasmonic material within the waveguide. And the last one is the performance of the plasmonic material based silicon optical modulator can be improved in terms of the performance matrices, which is IL, ER, FOM, and EBIT by carefully selecting or utilizing the device dimensions with suitable selection of plasmonic material used in the device. Now here we can see the objective of the thesis and the methodologies used to achieve the objectives. So here the first objective was to develop a mathematical model for the directional coupler based silicon optical modulator. So whenever two waveguides are set in close proximity to one another, then the energy traveling in one waveguide couples with the other. And this coupling phenomena can be termed as couple mode theory, CMT. So we have addressed this couple mode theory to achieve this objective. Now coming to the next objective, that is to design the architecture of the optical modulator based on 2-core, 3-core hybrid plasmonic directional coupler. So here, a 2D and 3D analysis tool, COMSOL Multiphysics, is used to design the architecture of the optical modulator. Now the third objective was to optimize the device parameters like the extension ratio, looping concentration, coupling length of the waveguide, and refractive index of the material used. So here we have used the rigorous finite element method, FEM, which is used to optimize the output parameters based on the input parameters. Also, the Drude-Lorentz model is used to calculate the voltage-dependent permittivity of the plasmonic material. Now, the fourth objective was to evaluate the performance of the directional coupler-based silicon optical modulator. So the performance of the device were evaluated by optimizing the device structure in terms of waveguide width, height, length, and thickness of the plasmonic material used. And two different kinds of plasmonic material, namely indium tin oxide and vanadium dioxides, are incorporated in the silicon optical modulator, and their performances were observed. Now coming to our contribution of the thesis. So we have 3 contributory chapters. So now going to the first contributory chapter, that is the architectural design of silicon-based optical modulators. So here in figure 3a, which is the cross-sectional view of our device. So where this blue color indicates the SI waveguide and the gray color indicates the ITO layer. So the width and the thickness of the SI layer is 300 nanometer and the width of the ITO layer is 190 nanometer. Which is separated with Si by hafnium dioxide, which is of 5 nanometer thickness. And coming to figure 3b, it shows the top view of the device. So here, whenever an input signal is introduced to a longer waveguide, it is coupled with a shorter waveguide and comes out of the same waveguide. And this phenomenon is known as couple mode theory. Now coming to figure C, it shows the coupling phenomena of the waveguide when no potential is applied and when potential is applied. So when no potential is applied, so here in figure C, the energy traveling through one waveguide couples with the other and comes out of the same waveguide. However, when a potential is introduced, then what happens due to the material characteristic of ITO, most of the signal or the energy is absorbed by the ITO-HFO2 layer. That's why absorption or loss occur whenever a potential is introduced to the waveguide. So this absorption or loss can be shown by this figure 3D. Here we can see that the real part of the ITO's permittivity, which is indicated by the black line, decreases, and the imaginary part of the ITO's permittivity, which is indicated by this red line, increases with increase in applied potential. So at around 2.3 volt, which is around here, the real part of ITO's permittivity, that is the black line, reaches 0. So this is known as the ENZ condition or epsilon near 0 condition. So at this condition, the behavior of ITO changes from a dielectric state to a metallic state. Therefore, at around this region, that is 2.3 volt, the ITO layer absorbs the energy. And this characteristic of ITO can be governed by this equation, that is equation A, B, and C. So here we can see that in equation A, the permittivity is equals to epsilon infinity minus omega alpha square by omega into omega plus I tau, where omega p is the plasma frequency, tau is the electron scattering rate, which is equals to 1.84 into 10 to the power 14 radian per second. And again, this plasma frequency can be calculated from this equation B, which is equals to root over n e square by epsilon naught m star, where m star is the effective mass of an electron and n is the carrier concentration, e is the charge of an electron, and epsilon naught is the permittivity of free space. Again, this carrier concentration can be calculated from this equation, where N naught is the bulk free carrier concentration of ITU, Vg is the applied potential, KHFO2 is the permittivity of HFO2, which is 25, THFO2 is the thickness of HFO2. So with regard to our figure A, here the thickness of HFO2 is 5 nanometer, and TACC is the accumulation layer. So now coming to figure 3E, here we can see the on-state and off-state of the device for the entire C-band wavelength range from 1500 nanometer to 1580 nanometer. Here the black line indicates the off-state and the red line indicates the on-state. So from here, we can calculate the extinction ratio, that is the blue color line. So extinction ratio can be calculated from this off-state and on-state losses, which is equals to ER equals to insertion loss at off-state minus insertion loss at on-state. So at around 1550 nanometer, which is the low loss optical window, we observed that at 1550 nanometer an ER of 8.25 dB was observed for our device. And this work has been published in the second international conference on advances in electrical, electronics and system engineering, ICA EESA in 2019. So now coming to the next slide, this is a structural design of electro-absorption modulator based on modified sidewall angle. So here in figure 4A, we see the structure of the modified sidewall angle based EM. Here the placement of the plasmonic layer and the dielectric material is at a certain angle, that is theta. So here theta is equals to 51.34 degree. So here by doing so, we have observed its performance matrices, and the height of the waveguide is 0.34 and the width of the waveguide is 0.32 micrometer. So coming to figure 4B, it shows the change in permittivity when there is an increase in carrier concentration for the device. So we can see that at a carrier concentration of 6.445 into 10 to the power 26 per meter cube, the ENZ condition for this device is achieved. That is around 6.45 into 10 to the power 26 meter per cube. So this carrier concentration corresponds to a particular voltage. So that voltage is shown in the inset of this figure 4B. Here we can see. So here with increase in applied potential, the carrier concentration increases since it is proportional to each other, as we have seen in the previous equation, that is equation number C. So here at around 4.45 volt, we achieve a carrier concentration of 6.45 into 10 to the power 26 per meter cube, which is the ENZ condition for this device. Now coming to figure 4C, here it shows the refractive index of ITO. That is a change in refractive index of ITO with increase in carrier concentration. So this graph is calculated from the permittivity. So we know that permittivity equals to n minus ik whole square. From that equation, this refractive index for the ITO is calculated. So in this work was published in Optic International Journal of Light and Electron Optic, volume 202. So now coming to the results and discussions on the mode profile of the device. So here we can see that figure 5A shows the TE mode and figure 5B shows the TM mode. So here figure 5A shows the on-state and off-state for TE mode, and figure 5B shows the on-state and off-state for TM mode. So from figure 5C here, we can see that with increase in carrier concentration, the MPA, that is a mode power attenuation, or it is also known as loss for the device, changes. So at around this region, say 6 to 8 region, the MPA for TM mode is maximum, that is for off-state, and the MPA for TE mode is minimum compared to TM mode. So in off-state, we want our device to absorb maximum amount of light. So in off-state, what we want is that we want higher loss for TM or TE mode in off-state. So here TM mode is providing higher loss for off-state. Therefore, we go for TM mode propagation of light in our device, since the loss in TE mode is less compared to TM mode. Now coming to this figure 5D, here we can see the MPa versus the carrier concentration graph for effective refractive index, which is shown on the right hand side, and for the TM mode, which is shown in the left hand side. So this TM mode graph is same as shown in figure 5C. However, I have included this graph in order to show a comparison between the TM mode and the effective refractive index. So here we can see that there is an abrupt change in the effective refractive index around this region, say from 6 to 8. This is because of the change in material characteristic of ITO from a dielectric material to a metallic material here. So but if we further increase the carrier concentration from say 8 into 10 to the power 26 per meter cube, again the graph of effective refractive index starts to decrease. This is because whenever epsilon, that is the permittivity of ITO, shifts away from 0, then it tends to change its states from metal state to dielectric state. Only around this region, say 6 to 8, it changes its characteristic from a dielectric to a metallic state. Beyond this region, again it becomes a dielectric material. Coming to the next slide. So this slide 5, figure 6a, it shows the mode power attenuation versus the sidewall angle. So with increase in sidewall angle, that is theta, which we have shown in our figure, what is the change in the MPa over the, what is the change in the MPa is shown in this figure. So here we can see that with increase in the sidewall angle, for the on state it is almost minimal, and for the off state it changes and it is maximum around 45-degree angle. But however, we have chosen the sidewall angle of 51.34 degree for our device. This is because we want to maintain a good relation between the ER and FOM, and moreover, since we are optimizing our device, so we want equal or same value for all the device structure. Therefore, we choose 51.34 degree as a sidewall angle for our device. Now coming to this figure B, here we can see that with increase in waveguide width, there is a change in the MPa or loss. So here from 0.20 to 0.30, the loss is high in both on state and off state. However, in on state, the loss is less from 0.30. So therefore, we have to choose a value from this region to this region. But in the off state, the loss is increasing from 0.30 micrometer. So for our device, we have chosen the waveguide width of 0.32 micrometer. This is because at 0.32 micrometer, we are gaining a higher value of MPa at off state. Because if we go for higher waveguide width, then what will happen? We will achieve higher value of MPa at off state, but the MPa for on state will also increase. That is, at present, the value of off state, the value of MPa at off state around 0.32 micrometer is around
Himanshu,
6.7.
be
Yes, sir.
brief. Sorry, be brief.
Okay.
Okay, don't go too much in detail. Be brief. Okay, summarize the things.
Okay. So here we have chosen 0.32 as the waveguide width. Now coming to figure 6C, here it shows the effect of increase in thickness of ITO on the MP of the device. So with increase in thickness of ITO, the insertion loss or the MPa increases for offset, whereas for the onset it is almost minimal. And here inset we can see that with increase in thickness of HFO2, the MPa increases and it is maximum around 5 nanometer. Therefore, we choose 5 nanometer as a thickness of HFO2 in order to achieve higher performance matrices of extinction ratio and figure of merit. So this extinction ratio and figure of merit can be calculated from this equation D. So here FOM is the figure of merit, which is equals to ER by IL, where EL is the extinction ratio and IL is the insertion loss at on state. So this can be calculated if the insertion loss at off state and on state is known, which is signified by this alpha off and alpha on, which is nothing but the IL at off state and the IL at on state. Now the modulation speed can be calculated from this equation E, where F is equals to 1 by 2 pi RC, where R is the resistance and C is the capacitance, and the energy consumption per bit can be calculated from this equation, that is EB equals to 1 by 4 C into delta V square, where delta V square is a change in applied potential. Now here coming to figure 7a, here figure 7a shows the change of insertion loss over the entire wavelength range for both the off state and on state.
Tell the significance of these graphs instead of explaining the graph itself. Okay, tell the significance or impact in a brief. Explanation you
here,
have already written in the thesis as well as in your article. You try to supplement. Okay, try to tell the significance of these graphs. Okay,
okay.
go ahead.
So from these graphs, we're calculating the on-state and on-off-state at 1.55 micrometer. So from this, we can calculate the ER and FOM, which is the extinction ratio and figure of merit. So the extinction ratio and figure of merit for a device around 1.55 micrometer was found to be 6.76 dB per micrometer. That is the extinction ratio, which is denoted by this black color line, and it is shown in the left-hand side y-axis, and the right hand side y-axis shows the figure of merit, which is around 422. So now this is the table which shows the comparison of our device among other contemporary ITO based modulator. So here this red color or the highlighted one shows our proposed device. So here we can see that our proposed device has an extension ratio of 6.7, which is better than most of the device except this reference 26, which is a little bit higher, and the loss at on state is very low in our device as compared to most of the device except this reference 9, and the FOM is high as compared to most all the devices in this table, which is around 422, and the energy consumption per bit is 6.8 femtojoule per bit. So now coming to the summary, so an electro operation.
You mind should just hold on, go back to earlier slide.
Yes, sir.
Yeah, this figure of merit has to be indicated with some unit.
No, sir, no, sir.
What is the unit?
So there is no unit for figure of merit.
Yeah, and for this ER.
ER, this is dB per micrometer, decibel per micrometer.
Yeah, no, you have claimed that 6.76 is the ER.
Yes, sir.
What is actually impact of your ER?
So actually, ER signifies that how much difference is there between the off-state loss and the on-state loss.
Correct. Now,
Because-
can you link to your design of a coupler which you have done? What care you have taken and how this is actually achieved?
Okay, sir. Okay, this is the design.
Yeah,
So here, sir.
Yeah.
Yes, sir.
You can speak directly that we have seen already, and I think given you sufficient number of corrections also.
Yes, sir.
Yeah.
So here what we are doing is that we are optimizing the structure of the device in terms of waveguide width or waveguide length. Here we can see. So we are optimizing our device structure in terms of sidewall angle, waveguide width, and thickness, and waveguide height. So from here we are calculating the off-state and on-state loss. So this off-state loss means whenever we are applying a potential, that is absorption occurs in the waveguide. So minimum amount of light should be allowed to pass through the waveguide, and maximum amount of light is allowed to absorb. Whereas in the on state, we're applying no potential. So in that phenomena, in that situation, we want our waveguide to absorb no amount of light. But however, in waveguide there are some absorptions, and this ER it shows the difference between the off state and on state losses. So means higher the value of ER, so better the performance of our device.
Okay. Go ahead.
Okay. So summary, coming to the next point, here the plasmonic material indium tin oxide has been characterized in terms of permittivity as a function of applied potential, and the device was investigated in terms of T and TM mode. Also, the investigated device showed enhanced performance in terms of ER, FOM, IL, and EBIT. So coming to the next contributory chapter of our thesis, this is the comparative analysis of VO2 and ITO based electro-absorption modulator. Here figure 8 shows the cross-sectional view of the device. Here this green color and black color line indicates the plasmonic and dielectric material. So what we have done here is that we have used two kind of material as plasmonic material. It is the indium tin oxide and the vanadium dioxide. And after that we have compared their results in terms of their performance matrices, and also we have compared with other contemporary devices having VO2 and ITO as the plasmonic material. So here in figure 8b, it shows the on-state and off-state for the device for vanadium dioxide as a plasmonic material, and the refractive index of vanadium dioxide is shown in this figure at metallic state and insulator state. Now, if we see this figure C here, it shows the effect of increase in length on the IL of the device. So with increase in length, the IL increases for both on state and on off state as length is proportional to loss. And here in the insert, we can see it shows the on state and off state losses for the device. Where in on state, most of the light is allowed to pass through the waveguide, and in off state, most of the light is absorbed. And this work was published in this Optic Communication Journal, and this paper was cited by around eight other papers. So here in figure 9, we can see this insertion loss over the waveguide width, insertion loss versus the waveguide width. So here we can see that maximum insertion loss is observed around this 400 nanometer. Therefore, we have chosen 400 nanometer as the waveguide width for our device. Also here IL for our device over the entire wavelength range from 1500 and 1580 nanometer is shown. But however, since we are using the application wavelength of 1550 nanometer, so at 1550 nanometer, we are observing their performance in terms of this offstate and on-state. Also here the insert shows the TE and TM mode over the entire wavelength range for on-state. Here we can see that here this black color line, there is a TE mode. It is maximum as compared to TM mode. And in TM mode, it is very minimal. So at the on-state, we want our device to absorb less amount of light, which is shown by the TM mode, which is absorbing very less amount of light. But in case of TM mode, the absorption is much higher. Therefore, we go for TM mode light propagation. Now coming to figure 9C, here it shows the effect of increasing thickness of VO2 on the IL of the device. And here the inset, it shows the different thicknesses of VO2. That is 20 nanometer, 30 nanometer, 40 and 50, where it shows the off-state and on-state. Here, the thickness of VO2 we have chosen is around 4 nanometer. This is because if you go for higher thickness of VO2, then it will increase the device footprint, as well as we will achieve very higher value of insertion loss at on-state. Therefore, we choose a minimum value of 10 nanometer. Now coming to the next slide, this is the characterization of indium tin oxide based EM. So here figure 10A shows the on-state and off-state of the device for the indium tin oxide based EM. At off-state, we can see that maximum light is absorbed by this ITO layer. Now coming to figure D, it shows the effect of increasing thickness of ITO on the IL of the device. So here we can see that the thickness increases up to 20 nanometer, and then it increases again for the offset. And here we have chosen 10 nanometer as the thickness of ITO because of two main reasons. One, the first reason is that to achieve the same amount of difference between the offstate and onstate, we have to go for higher value of thickness. It is around 14 nanometer. So therefore, with lower thickness of ITO, we are achieving the same difference between the offstate and onstate. Therefore, we are choosing this 10 nanometer as a thickness of ITO. And the second reason is that since we are comparing our device with the VO2 based device, where we have chosen 10 nanometer as the thickness of VO2, therefore we have chosen this thickness, that is 10 nanometer as a thickness of ITO. And coming to figure 10C, here it shows the effect of change in waveguide width on the IL of the device. So here, from this graph, we are selecting a suitable waveguide width, which is around 400 nanometer. Because we can see that the IL of offset increases, but from 400 nanometer, it is almost constant. Therefore, we choose this 400 nanometer as the waveguide width to achieve maximum ER and FOM. Also, this figure 10D, it shows the loss at offstate and onstate over the entire wavelength range from 1500 to 1580. So since we are using this 1550 communication wavelength, so at 1550 communication wavelength, the insertion loss observed at offstate is around 3.09 dB per micrometer, and at onstate it is around 0.025 dB per micrometer. Now coming to the extinction ratio for both the VO2 and ITO based devices. So this extinction ratio was calculated from the insertion loss graph for the on-state and off-state over the entire wavelength range. So here at 1550 nanometer, the extinction ratio for VO2 based EM is around 5.85 dB per micrometer, and for the ITO based EM, it is around 3.07 dB per micrometer. And now coming to 11B, the FOM for VO2-based CEM at 1550 nanometer is 8.98, and the FOM for ITO-based CEM at 1550 nanometer is 122. Now here, this table shows the comparison of our investigated ITO-based and vanadium dioxide-based EM along with other contemporary vanadium dioxide and indium tin oxide-based EM. So here we can see the insertion loss for our device was minimum for this ITO-based EM, which is around 0.025 dB per micrometer compared to most of the devices. Also, the extinction ratio for the vanadium dioxide based CM, which is around 5.85, is maximum as compared to most of the devices except this reference 37, which is 8.9. And the FOM for the ITO based EM is higher, 122, than all the other devices. And the energy consumption per bit for the ITO based EM is around 178, and for the VO2 based EM is 400 femtojoule per bit. So coming to the summary, so here we have investigated two plasmonic material-based electron modulator having indium tin oxide and vanadium dioxide as a plasmonic material, and both the devices have been compared in terms of their performance matrices. And also the ILER FOM for both the modulators were 0.651 dB per micrometer, 5.85 dB per micrometer, 8.98 respectively for the VO2 based CM, and 0.25 dB per micrometer, 3.07 dB per micrometer, 122 respectively for the ITO based EM. Now coming to the third contributory chapter, which is the V-shape ITO based electro-absorption modulator. So here figure 12a, it shows the cross-sectional view of the device. So here we have placed the plasmonic and the dielectric layer in a V-shaped fashion. Therefore the name the V-shape ITO based EM is given. And here we have taken two different heights, that is of 350 nanometer and 220 nanometer. While keeping these heights, we have observed the performance matrices and evaluated their performances with other plasmonic material-based devices. Here, figure 12b shows the on-state and off-state for the device with 350 nanometer waveguide height. And figure 12c, it shows the effect of increasing thickness of ITO for both the off-state and on-state losses. For our device, we have chosen 12 nanometer as the thickness of ITO because we can see that maximum insertion loss at offset is observed around this region, that is 10 to 15 nanometer. Therefore, we have taken an optimum value, that is 12 nanometer, as the thickness of ITO. Now, coming to figure D, here we can see that maximum loss or maximum difference between the on-state and off-state is observed around this region, that is 320 nanometer. Therefore, we have chosen 320 nanometer as the waveguide width for our device. Also coming to figure 12e, here it shows the height of the waveguide. So since at the off-state, maximum loss for our devices observed around this region, that is 350 nanometer, because maximum loss at offset is observed around 350 nanometer, and for the on-state the loss is almost minimal. Therefore, we choose this 350 nanometer as the height of the waveguide. Similarly, by keeping the height of the waveguide fixed, that is around 220 nanometer, what will be the suitable waveguide width for the device is shown in figure F. So here, a suitable width for the device having a height of 220 nanometer can be observed from this slide, where we can see that maximum or the suitable height is 400 nanometer. Therefore, we choose 400 nanometer as the waveguide width for the device having a height of 220 nanometer. So this work has been published in the Journal of Modern Optics.
Himanshu,
Yes, sir.
what is outcome of these all four figures? Can you explain? In a
So from here,
2-3 sentences. Yeah, in one figure you are explaining thickness, another
yes.
one height of waveguide, third one is waveguide width, and fourth one is also waveguide width. So what you are trying to say here basically?
Okay. So
In
here we are,
all figure, common parameter is the insertion loss. Okay.
yes, sir.
However, x-axis is different variables like thickness, height, and waveguide width. So two waveguide widths are there. What is the difference between these two? Figure D and F, because
Okay.
parameter is common.
Okay. So first of all, we are keeping this y-axis insertion loss common, and the x-axis we are varying with thickness of ITO waveguide width, because insertion loss is a very important parameter to calculate the performance matrices of an optical modulator. Since we are calculating extinction ratio FOM, which are based on the insertion loss of the device, therefore we are calculating what will be the means we are optimizing the device in terms of extension, in terms of insertion loss.
So why it is important? Why insertion loss is important?
Because from insertion loss, we are able to calculate extinction ratio and FOM, which are very important parameters.
So what?
And also, since our insertion loss decides how much or describes how much loss is absorbed by the device. So if maximum loss is absorbed by our device at on state, then the
Now,
device is not
from
suitable.
modulator point of view, you tell, from modulator point of view, you have to tell. You are
Yes,
going
sir.
to design, you are designing a modulator. In modulator, switching is important. On off is
Yes, sir.
important according to the modulating signal. And to have efficient on and off, that is the switching mechanism, this insertion loss calculation is essential. You have to tell like that.
Okay,
From
sir.
modulator point of view, okay, insertion loss, extension ratio, figure of merit, these are all technical terms, but you have to, ultimately it is leading to on off switching. That is the modulation, and which is the task of your modulator. Okay,
Yes, sir.
yeah, you go ahead.
Okay, now coming to the next question, that is why I have used this different waveguide width, because as I have told earlier, here we are comparing two devices. So one device is having a waveguide height of 350 nanometer, and the other is having a waveguide height of 220 nanometer. So for this 220 nanometer, what will be the suitable waveguide width? This is shown in figure 12F. So for the 220 nanometer waveguide height device, the suitable waveguide width is 400
But
nanometer.
what is the so peculiarity about 220 nanometer? And what is
Because
this 330 nanometer? From where this figure comes?
because in the current technology, the couplers we're using are of 220 nanometer.
And what about 350 nanometer?
350 nanometer, these are we are designing, but for 350 nanometer, the couplers we have are not available. Means we have to design that coupler.
Okay, go ahead.
Okay, so here figure 3, it shows these devices. So these are different devices with different placements of plasmonic material, as well as different kinds of material has been used. So we are comparing our devices along with these devices, that is device A, B, C, D, E, F, and G, in terms of their structural parameters as well as performance matrices. So this table 3, it shows the structural parameters of different contemporary ITO-based optical modulator. So here the highlighted part shows our investigated modulator, which is having a height of 220 nanometer and a height of 350 nanometer. So here it shows the thicknesses of ITO for different materials, also the height of the waveguide for different materials, and the width of the waveguide for different material for different modulators. For our device, for 220 nanometer waveguide height, we have used 400 as the waveguide width, and for the 350 nanometer waveguide height, we have used this 320 nanometer as the waveguide width. Now coming to figure 14a, it shows the IL for both on-state and off-state over the entire wavelength range. So at around 1550 nanometer, we have observed a loss of around around 7 dB per micrometer for offset, and for the onset it was around 0.31 dB per micrometer. And coming to figure 14b, here it shows the ER and FOM for the V-shape EM with 220 nanometer waveguide height, and for the V-shape EM at 1550 nanometer, the extinction ratio was observed to be around 7.02 dB per micrometer, and the FOM was observed to be around 226. Now for the EAM with 350 nanometer waveguide height, the IL at offstate was observed to be around 11.06 dB per micrometer, and at offstate it was observed to be around 0.025 dB per micrometer. So from here we are calculating the ER and FOM, which is equal to 11.04 dB per micrometer for the 350 nanometer waveguide height device, and the FOM is around 441. So this is a table which shows the list of devices which we have compared along with our device, that is the 220 nanometer base EM and the 350 nanometer base EM. So here we can see that higher extinction ratio is observed for the 320 nanometer base EM, which is around 11.04 dB for our 350 nanometer base device, and the lower insertion loss is observed for a 350 nanometer height device, which is around 0.025 dB per micrometer as compared to most of the devices except this reference line. And the figure of merit is also very high compared to other devices for the 350 nanometer base EM. And the energy consumption per bit for the 220 nanometer base EM is 112, and for the 350 nanometer height is 106. Coming to the summary of the V-shaped EM, the V-shaped ITO-based plasmonic EM has been designed with different waveguide height for 220 nanometer and 350 nanometer, and their performance has been evaluated in terms of IL, ER, FOM, and EBIT respectively. And the ER, IL, FOM, and EBIT for the devices are 7.02 dB per micrometer, 0.031 dB per micrometer, 226 and 112 femtojoule per bit for 220 nanometer base EM, and 11.04 dB per micrometer and 0.025 dB per micrometer, 441 and 106 femtojoule per bit for 350 nanometer base EM respectively. Now coming to the conclusions of the thesis work. So a modified sidewall angle plasmonic base EM has been designed and investigated. Also, the material characteristic of ITO was investigated in terms of the refractive index, plasmonic material, carrier concentration, and permittivity. And two different modulators with ITO and VO2 plasmonic material base EM has been designed and characterized, and their performance matrices were evaluated in terms of IL, ER, and FOM, and energy consumption per bit. Also, a V-shaped ITO based EM was proposed, simulated, and investigated for two different heights of 220 nanometer and 350 nanometer, and the effect of change in the structural parameter on the performance of the device were observed. And the investigated modulators can be very promising in the next generation CMOS photonic integrated circuits. Now coming to the limitations of the present work discuss different performance matrices like insertion loss, extinction ratio, figure of merit, energy consumption per bit. However, the losses related to scattering and radiation were not discussed, and miniaturized devices integrated with plasmonic material have led to the family of novel nanoplasmonic devices. The plasmonic material-based EMs can be used in photonic integrated circuits. However, the present work doesn't discuss about the data rates. And the present work discusses different modulator design based on ITO and VO2 plasmonic material. However, other plasmonic materials like graphene, gallium lobe, zinc oxide are unexplored in the present work. Now, the future scope of the thesis work are that further exploring the device structural parameters like waveguide width, waveguide height, length of the waveguide, polarized and insensitive modulators based on plasmonic material can be designed and implemented. Also, incorporation of other plasmonic materials like graphene and gallium lobe, zinc oxide, etc. in a silicon optical modulator structure and observe its performances. And different structural design like slot waveguide, cross-slot waveguide, and T-shaped plasmonic-based waveguide can be used to design and implement an EM with plasmonic material. And the last future work is the fabrication of the investigated devices and incorporating the devices in photonic integrated circuits. Now, these are a list of journal publication. The work of the first chapter was published in this journal, that is Optic International Journal of Light and Electron Optic elsewhere. And the work of the second chapter was published in this journal, that is Optic Communication Journal of elsewhere. And the work of third paper was published in this Journal of Modern Optics of Taylor and Francis. And these are the conference paper publications. One was published in the Third International Conference on Microwave and Photonic, ICMF 2018 in IIT Dhanbad. And the other one is the proceedings was published in the proceedings of Second International Conference in Computing and Communication System, which was later published in lecture notes in Networks and Systems, Springer. And these are some of the papers which were presented in the conferences. So these are the references. So here this reference, this was one of the base paper for the first chapter. So we have highlighted this reference to show it. Now I'll come to the acknowledgement. So many significant personalities have helped me throughout this journey, and mere words cannot express their effort to help me throughout this journey. First and foremost, I would like to thank my supervisor, Dr. Subhash Arya sir, for guiding, believing, and supporting me in every step of the way, without whom I would have never reached this stage. I'd also like to thank all the faculty members and non-teaching staff of Department of Electronics and Communication Engineering School of Technology, Northeastern Hill University, for their constant support throughout this journey. I also like to thank my PhD evaluation committee members for giving and sparing their valuable time. I also acknowledge the help and support that I have received from the members of Lightwave Communication Systems Laboratory in regular online session. At last, I would like to thank all my friends and family for their constant support throughout the journey. Thank you.
Yeah, Himanshu, can you, it was a nice presentation. Can you go to slide number 23, please?
26, sir.
23.
20. Okay.
Yeah, now you're given a summary of ITO and V02. What is your recommendation? Actually, one slide before also you can go so that it will help you. Just go back. Yeah, now you can have a comparison. What exactly you want to recommend, whether ITO based design or VOTO based design?
Okay. So first of all, I want to tell that achieving all the parameters, so achieving a good value for all the parameters is very rare, because we can see that here we have achieved lower value of
Good, good.
insertion loss.
We can see it, but what is that magic you have done it to achieve for ITO? You claimed the figure of merit as 122, and
Yes, sir.
you just have a glance particular column for FOM, and it is a great boost as such. So, what is that
Yes.
the care you have taken in design to achieve this particular 122 figure of merit?
So we have done a structural optimization.
Yeah, that structural optimization. I would like to have your opinion on page number 31 or slide number 31 later. But here also you can see VOT design earlier. You are shown with the row number 5 as 250. Somebody has published that work, the reference number 18, and then whatever investigation you have done, suddenly there is a rise from 250 to 400 as the EBIT. How this is achieved?
Sir, this is because of the placement of ITO material. So in here we have placed the ITO layer along with a dielectric material that is HFO2, and the placement is in a rectangular shape if we see the figure of our structure. So in terms of that, whenever we are optimizing our device structure in terms of thickness of ITO or thickness of the plasmonic material and width of the waveguide, there is a change in their performance matrices. And this performance.
Again, Himanshu, I request you to keep that whatever you spoke and please summarize it on slide number 31 later. Okay, now you can go to slide number 25.
Yes, sir.
Yeah, here you have shown something that the publication is done in the Taylor and Francis, the Journal of Modern Optics. So, do you
Yes, sir.
feel that Taylor and Optics is above the elsewhere because you had a publication earlier in those journals, and suddenly
Yes,
you
sir.
accepted it to a Taylor and Francis? What is the reason?
Sir, actually, Taylor and Francis is also a SCI index journal, and this elsewhere also is a SCI index journal. So
Yeah,
I prefer
can you
SCI index journal.
see, all research scholars even are wanting that whether it is better to publish at Teller and Francis or elsewhere or any. They are in search of venues. Can you guide them?
Sir, according to me, from my point of view, we should see whether it is SCI index or not, and we should see how much impact factor it is having.
Yeah, impact factor anyway will come say after a few days of direct, publishing the work, that
Yes,
will
sir.
vary. Okay, then can you please go to slide number 26.
Yes, sir.
Okay, the you are given design. Okay, 27.
Yes,
And
sir.
here exactly you're given a comparison uh, with different heights 220 and 350. Here
Yes, sir.
you have given different say parameters also, and outcome of which one you recommend, which height is optimized, or I can take that particular height which will give me better results.
So as per my knowledge, the current technology is having the current technology is 220 nanometer as per my knowledge. So if we go for 350 nanometer, obviously this 350 nanometer is giving a better performance matrices. But if we go for 350, then we will have to design our coupler.
Okay.
But
At the
for
end, I
220
will
nanometer,
just
yeah.
remind this to you. Okay, please go to next slide. That is 28.
Sir, Himanshu, actually here a silicon wafer which
Yes,
is
sir.
commercially available for IC designing has 220 nanometer of thickness. So you have opportunity to buy it commercially having very less price. So that is why 220 nanometer was explored. However, if you go for 330 nanometer, then you have to specifically order that silicon wafer manufacturer, which increases your cost. So that is why these two exercise has been done. So you have to split it this way. Commercial aspect has been taken care as well as device performance has been taken care. Both. Yes, you go ahead also.
Yeah, this slide number 28, Himanshu. One side you are comparing ER dBs per micrometer, and other side you are putting FOM.
Yes, sir.
What is that exact relation between these two parameters?
So actually, extinction ratio is equals to the insertion loss at off state minus insertion loss at on state.
See, one is having a unit, other you said that it is unitless. How can we
Yes, sir.
compare? Or two separate graphs would have been better.
So two separate have been better, but here actually this is I'm combining two separate graphs only
Then
because
there
one
has to
is
be a relation between the ERDB micrometer, some formula you are defined.
yeah,
Then
yeah.
there has to be a relation between both the say expressions for ER and FOM, which you are not explored anywhere. Another problem I am facing here is, see, most of the third window designs are restricted to 1500 to 1550 nanometer, and people are not trying for the bands above which now slowly whole world will be going for the towards the higher nanometers as such. The to incorporate higher, say, exploration of bandwidth and data rates. But at present, people are concentrating only on 1550 to 1550 nanometer. And with that perspective, can you recommend your design for a particular, say, operating wavelength?
So here actually we have designed only for this 1550 nanometer.
Yeah.
But if we explore further in terms of operating wavelength, say you are talking about beyond 1580 nanometer or beyond 600 nanometer, for that we have to see
So, what do you
see
recommend?
wavelength. Yes, sir.
What do you recommend the operators to use the lambdas above 1550 or something else?
So if that wavelength, suppose now 1550 nanometer is having less loss, it is around 0.2 dB per micrometer.
Yeah.
That's why most of the applications use 1550 nanometer. If some other wavelength is there where the loss is less than 0.2 dB per micrometer, then we can go for that wavelength.
Okay, Himanshu, please go to slide number 31. Yeah, then can you defend whatever statement you have made, the last statement?
The investigation of modulators be very promising in next generation CMOS photonic integrated circuit. Actually, the current CMOS technology, our plasmonic material-based silicon.
I'm having the problem with the can be.
Yes, sir.
His statement says it is can be.
Yes,
Yeah,
sir. Yes, sir.
it
So,
should be. Yeah,
you see, once you finish your PhD, we expect that yes, it has to be a bold statement, and
yeah,
the can be word will come in future scope, not here.
Okay, sir.
Whenever you are presenting, you present with a stress, and that should not be with a this tense sort of thing. Anyway, okay, I think Arya sir, I
yes,
first want to congratulate you and then to your student good presentation, and hope he has incorporated all changes which
yeah,
are suggested. One thing only I want from Himanshu. Himanshu, I have given certain questionnaire that to be addressed. So if you are having the answers, you can show it to this August forum that yes, something was suggested and you have done it. And please see that we expect post say submission publication also. Is there any publication which is in pipeline?
No, sir.
Yeah, this tempo should not die down. That is the thing which Professor Arya also will expect, that you should continue publishing it, and not
Yes, sir.
that your submitted PhD system will take its own time, give you so many corrections. That is, but publishing after submission is also important.
Yes, sir.
yeah. Thank you, sir. Thank you very much, sir, for giving. In fact, what I used to keep telling to Himanshu, you have also helped me to draw the attention of researcher on that aspect, which many times people do not do. And you have extensively, yeah, read the thesis and give a lot of suggestions for the quality improvement. That is great. I am very thankful. And the questions which you have asked very pertinent. And Himanshu, you have to come with better, because this kind of question will come again and again whenever you are going for the interview or any other places also. So after that, please address those questions which you have received via me, asked
Okay.
by the Professor Bhosle sir.
Yeah, sir, Arya sir, with your permission, now forum is open for others. They can ask. Uh,
Yeah, after addressing these questions which you have asked,
yeah, yeah.
after that, yeah, then we can invite question from others also, because that is streamlined questions. Yes, Himanshu, go ahead. Address this
So
question.
the first question was, in the current all optical systems, what would be the impact of your research as far as speed of operation and bandwidth issues are concerned? So answer for this question, we have written it like that. The silicon optical modulators have been commercially deployed and have demonstrated good performance. However, plasmonic based modulators are in the early state of their development. As far as speed of operation is concerned, the investigated devices in the thesis show a modulation speed of 231 GHz, 52.6 GHz, and 14.8 GHz for the modified sidewall angle modulator, VO2 based EM, and 350 nanometer height based EM, respectively. And coming to this bandwidth issue, the plasmonic based modulators are efficient for TM mode of light propagation, and other kinds of modulators such as ring resonator, MZI, Maxenter interferometer, utilizes TE mode of propagation. So utilizing both the devices along with polarization division multiplexing modulation, we can achieve high spectral bandwidth. So, and this is the question number two. Do you think the work done in your research is going to be beneficial to the optical industry? The answer is yes. The silicon photonic market is increasing rapidly and is expected to have a compound annual growth rate of 40% from 2019 to 2025 to meet the industry's demand, as shown in this figure 1A, which I have shown in the first introductory slides. And also, our research will help to fill the gap of the electronic and photonic devices as shown in figure 1b. So here there is a gap for electronic and photonic which is filled by the plasmonic material based devices. So our research is going to be beneficial in that area. Now coming to the third question was, while upgrading the current system all over the world, what is the cost effectiveness of the proposed research work? So since the devices proposed in the thesis is CMOS compatible, provided the establishment of new foundries for indium tin oxide and vanadium dioxide fabrication, we can go for multi-project wafer semiconductor arrangement, where a multiple number of chips can be designed in a single wafer, which will be very cost effective. So these were the questions.
Himanshu, you just read. You should explain. The question should be explained in your own wordings.
Sir,
Writing is okay.
okay, it is, yes, tried. Okay, sir, few of my colleagues present over here.
Yeah,
They
great.
want to just interact with him. And yes, from my side, it is over. And congratulations, Himanshu.
Thank you, sir.
Yeah. So, my colleague, Dr. Vivek, is here. He wants to ask you something. I'll just shift my seat so that he will answer.
Yeah, sure, sure. Most welcome.
Excellent work, Himanshu. I have few
Thank you,
queries.
sir.
Yeah, I have few queries, and the first is very basic. That what are the losses and speed you have targeted for your first modulator which you have designed in very first work?
Yes, sir. So the losses for the very first one. So this one.
Yes.
Yes, sir. So the losses for the off-state is around minus 0.10 dB, and the losses for the on-state is around minus 8.35 dB.
Okay, so we can consider it around minus 9 dB.
Minus
When
9 dB.
because we when we use the modulator as a
Yes, sir.
for as a device which is transmitting, so can we consider it to be a overall offering the loss of minus 9 dB or overall loss
Minus
of
9
9?
dB. Sir, actually, suppose for the on-state, if you have 9 dB, then it will be around, it will be more, sir, actually 9 dB. It
Huh,
should be considered 8 minus 8.35 dB only. Because if losses increase by 0.2 dB also, then it is much higher.
much higher. Yes. So that was my actual question. And now, how this speed is related to this? I mean the data rate. Have you tried?
Okay, sir. Actually, I have shown in the limitations that we have not calculated the data rates, but speed has relation with data rate, so we will calculate this in future.
Okay, no problem. And the extension ratio you have commented. So will
Yes,
you
sir.
please highlight how extension ratio and these losses are actually interconnected with each other when we talk purely about modulator?
So actually, extinction ratio is the switching speed.
Yeah.
So switching speeds depends on the switching from on state to off state. So here we have calculated the losses at on state and off state. So for that, from there we are calculating the extinction ratio. So higher the value of extinction ratio, it means higher switching speed.
Yes.
So
So
it's
this
a
is
better performance.
yes. So these are going to be the minimum extension ratio you are going to offer, right? It can be
Yes,
higher than this,
yes,
correct?
sir, it can be higher. Yes,
This is the lowest configuration you are offering, but in actually when you design this modulator, it will be work very high, right?
it can work high because
Higher than that.
yes.
Yes. So this was my query, first query regarding your first work. Then second one is regarding EA modulator. So now can you highlight how much losses your EA modulator, I mean the designed version is going to offer?
So you are talking about this modulator.
Yes.
So here the losses at offset is around 6.78 dB per micrometer for offset, and for onstate it is around 0.016 dB
Okay. So how
per
much,
micrometer.
if I just say percentage wise, how much improvement you have done in your second work?
Improvement, sir.
Yes.
Sir, actually this is
Show your
improvement in
comparison table. Show your comparison table. From there you can show, because it was improved version of previous published work. Yeah, from
yeah.
here you can see.
So here from this table we can see here this reference number 25.
Yes.
Here we have taken this as a reference paper. reference number 26.
Yes. So this reference number 26 was published in which year?
This was published in 2018.
18 itself. Okay,
Yeah.
good. And now go to slide number 14, just one previous slide.
Yes, sir.
So if you just check here, yeah, if you just check here, your right hand side figure B is showing
Yes.
some variation in ER,
Yes, sir.
right, with respect to wavelength.
Yes, sir.
So if we say if we are using for WDM or any other application, if your device we are utilizing, then uh, what people expect is a flat ER line, right, or a minor variation in it. But your is nearly 2 dB of variation. So can you
Yes,
offer
sir.
something, or can you highlight some another criteria to the flat the line? So all the wavelength will have the equal amount of ER.
So that will depend on this structural optimization. For our structure, we are having this here.
No, as
So
far as your
the
structure is concerned, you have explained very correctly and it is very right. But I'm just asking you to, go a bit step ahead of this. You have already designed it. Your design is very correct. I'm not asking that. But there is a 2 dB variation. So can you do something on it, on top of it?
so I'll have to look on it, sir.
Okay. Since you are going to look, then kindly go into the break grating and check whether which particular periodic order, whether it is short one or longer. Not now, but you can explore it later. You can just go ahead and check. So ER value will be stable for all the wavelengths. So there will be
Exactly.
less non-linearity when you transmit in WDM and DWDM.
Okay, sir. Thank you for the information, sir.
Yes, and I have a final question, and that is on vanadium dioxide.
Yes, sir.
And how compatibly it is when we design it and when we manufacture it on chip, when you compare it with iridium, gallium, and silicon, indium, gallium, silicon, and when you compare with those modules, how compatible it is.
So in terms of fabrication, these plasmonic materials have some challenges because the existing CMOS technology means for a normal silicon optical modulator, existing CMOS technology we can fabricate, but for plasmonic material based electro-absorption modulator, say indium tin oxide, vanadium dioxide, so we have to go for CMOS fabrication, which is having new foundries because these materials might contaminate the clean room where we are going to fabricate. So such kind of new foundries should be there for fabrication of this plasmonic material based electro-absorption modulators.
Okay, so have you tried reaching them for fabrication purpose?
Sir, I went to ISC Bangalore and I was a member.
Program?
Yeah, I went to ISC Bangalore as a
Yeah,
part of INUP program.
yeah, INUP
Application.
program, right? Huh.
Yeah, yeah. So I got training there in Sense, that ISC Bangalore.
Okay.
So there means they have told some challenges are there regarding this plasmonic material.
Yes.
So, it will be a little bit difficult for fabricating at present, but however, in the future, it will be
Hey,
possible.
yeah, in future, everything is plasmonic only, as what
Yes, sir.
we can see, and many scientists have also said that
Yes,
since
sir.
it is offering very less area and high data rate. So, okay, thank you from my end.
Yeah, Vivek,
Okay.
thank
Thank
you.
you, sir.
I have another colleague who is actually.
Thank you, Dr. Vivek. Thank you, Dr. Vivek, for this, asking very brilliant questions and mind-boggling questions also, which compel to think. Yeah,
Hello.
Doctor. Yes.
Yeah, Himanshu. This is Dr. Prashant Bhosle.
Yes, sir.
I need to ask you one or two questions. Can you go to figure 5B? Yeah,
5G. Yeah.
yeah. You can see, yeah, in 5D, 5D. Okay.
Yes,
You
sir.
can see the aberrant change in the graph, right? For
Yes, sir.
so, don't you think this aberrant change will require extra energy and that can increase the heat dissipation or can damage your device or something?
So regarding this thermal stability, for that I don't have the adequate knowledge. But this change, regarding this change, it is because of the change in permittivity of ITO.
I know the
Yeah,
changes due to the physical property of the material, right?
yeah.
But if you are contributing to the science for some adding something, some your
Yes.
own contribution, which is increasing the MPa dB
Yes,
per
sir.
micromillimeter range,
Yes,
and
sir.
that can damage the device, then you should have knowledge about it. What parameters can control this abrupt change or sudden change?
The parameter which is controlling this change is the applied
And
potential.
can you control this slope of this graph in the red color?
Yes, sir.
Can you control the slope of this graph? See, the sudden change are due to, and the changes are not increasing exponentially. It is going deep
Yes.
and getting up, right?
Yes, sir. We can control, sir.
Yeah. What are the parameters which can make it smooth?
Smooth, sir.
Yeah. The
Uh,
sudden change, see, any physical material should not give a sudden change. It is a probability that it may damage or it may get some some permanent damage to that device or circuitry, right? For
okay.
that you always need a smooth switching throughout the
Okay.
whatever range you are considering, right? So here the sudden change may, will it damage your device, or can you control it, or is there any condition, precautions you have to consider while you applying your algorithm?
Sir, okay. Sir, I'll have to look upon it. I will look
Actually,
on it,
the
sir.
device is changing completely its behavior from dielectric to
Yes,
conductor.
doctor, right?
So there is no such question of damage of the material, because material characteristic itself is drastically changing from conducting to dielectric and vice versa. So whenever
There's an
material is
electrostatic
conducting,
difference between conduction
yes,
band and balancement, right? So the
yeah.
electrons have to jump from one band to another by taking energy, and suddenly carrier with the carrier concentration, it is taking more
No,
energy, right?
actually, this is case in semiconductor. A plasmonic material from dielectric to conductor.
Okay,
Okay,
right.
so dielectric to conductor. That is why you can see the sharp jump. Okay, so
Okay.
it's characteristics of plasmonic material that at a particular voltage,
Mhm.
which reflect to change in the concentration, and because of this change in the concentration, device is behaving at particular one voltage in dielectric, in another one
Yes,
conducting. So what happens whenever it is working as a metal, then entire light will be absorbed, no
right.
light is available. And
Yes,
whenever it is working as a dielectric, entire light is passing.
right.
So in this way we are achieving the switching. So
Fine.
yeah.
And another last question for you, Himanshu. Do you have some mathematical proofs for your contribution?
Mathematical proofs.
Yeah, you are optimizing the structure, right?
Yes, sir.
Optimization is kind of functional optimization for one parameter. So that entire thing, optimization is a mathematical term.
Yes, sir.
So if you have any mathematical proof, that I would like.
So we are using the Drude Lorentz model for this calculating the characteristic of ITO.
Okay,
So
fine.
further can be added that you can develop a compact model of your device, so that through mathematical modeling one can pass on this information to others.
Right.
Dr. Prashant, very nice question.
Thank you.
Thank you, thank you.
And one last question 14b. Can you go to it? Figure
So
figure
figure
14b. 14b.
14B. Okay, sir.
Yeah.
Okay, sir.
Both graphs are starting from different initial condition. The red one is starting from 3.5 and the black one is starting from 5.
Yes.
If you're comparing two algorithms or two whatever things, it should start from same initial condition, right? If I'm wrong, please correct me.
So actually, these are different parameters. That is, they are indicating different parameters. There are two axes. So this FOM is indicated by the right hand side y-axis, and the ER is indicated by the left hand side y-axis.
Okay, fine. Fine.
Okay,
Thank you,
sir.
Manchu. Thank you and
Thank you, sir.
congratulations.
Thank you, Dr. Prashant. Thank you so much for interacting and paying so much attention and asking the question. That kind of interaction makes our program live.
Right.
Sir, everybody is active here.
Yeah,
Yeah.
great.
Excuse me, sir, I have something to ask.
Yeah, doctor. Achala is
Welcome, Ashila madam.
Okay, thank you, sir. Himanshu, sir, you have worked, your work is very huge as much I can see, and you have presented it very well and very precisely, because in so much little slides present your entire PhD work is also a difficult thing. I do understand that. Okay, so what you will recommend as a future scope? Expect a little focused answer than whatever you have shown in the slides.
Sorry,
Future,
ma'am, I didn't get your question, ma'am.
uh, so what you will recommend as a future scope?
Okay, sir. So, ma'am, the future scope is to fabricate a device which I have designed, which I have shown in this presentation. So those are my first future scope, and the second was to incorporate other materials and other waveguide structures, like I have shown in the future scope slide, like cross-slot waveguide, T-shape waveguide, then polarized and insensitive modulator, based on plasmonic material, which are actually burning issue or new issue, we can say.
Okay.
So those are my future scopes.
And is there any publications after submission of your thesis? Are there any
Af-
publications after
After
submission?
submission, no, ma'am.
Okay. Okay. Thank you so much, and congratulations, Himanshu sir.
Thank you, ma'am.
Thank you, Achila madam. Thank you so much. Yeah, now floor is open to interact with the professor. Anyone else? We can write. Anyone else can write your question chat box also. I can read out on your behalf. However, it will be good if you can interact directly. Unmute your microphone and interact with researcher Himanshu Ranjan.
Okay, sir, I would like to go next. Himanshu, you have like stressed so much on this extinction ratio and this figure of merit. So I would like to know like how you are calculating this too.
So excitation ratio can be calculated if we know the on state as well as the off state of the device, because as I have shown in the equations, there is equation number D, I think. That is extinction ratio is equals to insertion loss at off state minus insertion loss at on state. And if you know the loss at both the states, then we can also calculate the FOM. So here, this alpha loss minus alpha on gives the extinction ratio, and if we divide it by alpha on, then it will give the FOM, that is figure of merit.
Acha, Himanshu, please add on how this F1 become unitless, because sir is asking now extension ratio. You are telling that dB per micrometer. Insertion loss is also dB per micrometer. Then
Yes.
after taking these two, how F1 become unitless?
So because both the FOM is a ratio of extinction ratio to actually FOM is the ratio of insertion loss at off state minus insertion loss at on state to insertion loss at on state. So this is the ratio of ER and IL.
Yeah, and ratio has no unit.
Yes, sir.
Yeah. Yeah, so Fajo, you could get basically whenever he is calculating the output when light is inserted and then calculating how much light is available at the output. So in this way, if that difference is telling about the loss.
Yes, sir. Yes, sir. Thank you, Himanshu.
Thank you.
And yeah, Balvinder is asking, can you tell me about E and Z condition, epsilon near zero condition?
So yes, ENZ means epsilon near zero condition. So this is a condition when the epsilon naught, that is the permittivity of the material, reaches zero. That's why it is termed as epsilon naught near zero condition. So for our device, the epsilon naught zero condition is around 4.45 volt, which corresponds to the carrier concentration of 6.45 into 10 to the power 26. So at this condition, the state of or the characteristic of plasmonic material, it is ITO, changes from a dielectric state to a metallic state. So this is the ENZ condition.
Good, good. Balvinder, any more, or you are satisfied with the answer?
No, sir. Okay, Himanshu, thank you and congrats for your presentation. It is a nice presentation. Thank you,
Okay,
Himanshu.
thank you very much.
Thank you for being here, Balvinder. Any more question?
Sir, from my side, no questions. Sir.
Okay.
Thank you.
Okay.
Congratulations to Himanshu and his
Thank you,
guide,
sir.
Dr. Arya.
Thank you, Dr. Jaydeep. So a lot of my department member are also here, and very, very happy and glad and thankful that Professor Bhosle sir has motivated his colleague, his department faculty member to be part of this PhD Viva seminar. He not being not only being a external examiner, but changing the entire entire research environment. And everybody has asked the question. It means they were looking very keenly, very interestingly, and that shows the success of work what Himanshu has done. Himanshu has, yes, in order to fabricate, he has visited INUP, ISC Bangalore, and tried to explore ways and means whether his device can be fabricated and cross-check how much difference is there in simulated result and fabricated result. But because of the limitation of the technology, he could not do. But near future may be possible. And Himanshu happened to be a Rajiv Gandhi Fellowship receiver given by UGC, a prestigious fellowship. So, and he has carried out a satisfactory work to me, although supervisor never to be satisfied. But I used to keep motivating him, and the valuable honorable members have also emphasized what I was looking from Himanshu also. So from my side, uh, best wishes and thank you so much, Professor Bhosle sir, our Dr. Upaman Subeda, Dr. Jaydeep, Dr. Juesh Binong, Dr. Shishanta Kabir Datta sir, and our students, as well as the way two institutions have joined together for making this. It's really makes some difference. So thank you so much.
Right, sir,
And now,
I want to correct you because three institutes. Dr. Achala Deshmukh is from Siagat, Pune, and
Arey wow, great, great. Thank you, sir. Thank you.
yeah.
Thank you. Welcome, Madam Achila, Madam. Gracing these occasions, your interaction and motivation really matters a lot to us.
Thank
Thank
you
you.
so much, sir.
And near future, please, I would like to invite, please come here in Shillong. Shillong is known as a Scotland of Northeast. It's very, very beautiful place, and you must visit at least once Cherrapunji, Shillong, and give us opportunity to host you, all of you, uh, to the extent of my best level. Uh, with this,
Thank you, sir.
with this, again, thank you so much. With permission of our external examiner and head of the department, if everything has gone well, I would like to declare, since Himanshu Ranjan Das has completed all official formalities and he has achieved the requisite qualifications and criteria to be awarded a PhD degree in Electronics and Communication Engineering on the title of Design of National Coupler-Based Optical Modulator. So I declare he can be awarded a PhD degree. So with this,
Sir,
yeah.
Dr. Arya, sir, let head of department, your head of department, colleague, Dr. Himanshu now. Sir, please.
Am I audible, sir?
Yes, sir. Yes, sir. Yes.
So congratulations, Himanshu. Okay. So we
Thank you,
are
sir.
really thankful to you that you have that means give a very good presentation and you could able to that means raise the level of the department. You have good publication, and I hope what the sir has already mentioned you will keep in your mind. That means after PhD also you should do your research and you should continue your publication. Okay, and I
Yes, sir.
hope I am sure that you are going to do the same. Okay, I also understand that because of this pandemic actually there is a gap, and because of that actually there is a that means flow mismatching, you can say. Okay, so the flow have been interrupted, so might not be you are not having any work right now. Okay, but I am sure, okay, with little effort, okay, you can that means bring your flow back and you can easily publish more publication. Okay, and congratulations and best wishes for your future life.
Thank you, sir. Thank you very much.
And obviously from the department side, okay, with permission from our external examiner, okay, we are going to recommend you actually for awarding the PhD degree. Actually, it's, the final award have been given by the Vice Chancellor, okay, from after recommending, okay, we are recommending it to the examination section. Examination section put up the file, and the final authority is the actually not Vice Chancellor, it is the Board of Research, that means Academic Council, but it is being ratified in the Academic Council, and Vice Chancellor used to approve it. And later on, he used to apprise it, or he used to ratify it in the Academic Council. So we are going to do the same over here. Okay, we are going to recommend your name, and again, congratulations, both of you, guide as well as the student.
Thank you,
Okay,
sir.
thank you from my side.
Thank you so much, sir, for being here and given us a platform. And as a head department, you have facilitated whatever help and other administrative cooperation was required to facilitate the research work carried out by Himanshu Ranjan Das. For that, we are grateful and thankful to you, sir, also. And
Yes, sir,
entire
it was my duty, sir. It was my duty.
yeah,
But
sir.
the main work have been done by both of you only. Okay, whatever I have done, it's my duty, sir.
Yeah,
I have
yes.
been appointed for the same, for that particular work only.
Yes, sir.
Okay.
So nice of you, sir. So with this, I think now since we I declared this as in earlier now when our Diman Kakati was presenting. So at that time, I correctly remember our dean has suggested us we have to declare. So I have declared although. So again, congratulations. And now I think we can address him as not officially, at least Dr. Himanshu Ranjan Das.
Yes, yes, sir. Yes, sir.
So congratulations, Himanshu Ranjan,
Yes,
and
yes.
for your
Thank you,
patient
sir.
5-year work you have presented in a very limited time. And I can understand you want to share each and every output in graph, that is but we were having less patience on that. So we can understand your zeal and enthusiasm towards your results that really a researcher loves. And today is the day which every researcher look into. So with this, thank you so much for being here. And from my side, invitation is extended to all of you, particularly VJTI, and to Madam Achla and others also, to visit Nehu Shillong as well as Cherrapunji and give us opportunity to host you.
Yes,
So
Thank you so much, sir. And congratulations, Dr. Himanshu.
Thank you, ma'am.
thank you, sir.
thank you.
With this, I think now we can sign off.
Yes, sir.
Yes, yes,
With
yes.
kind permission
Okay.
of our examiner. Okay, sir. Bye. Take care. Thank you
Yes, sir.
for
Bye.
being here. Thank you,
Yes,
everyone.
sir. Bye, sir.
Vinod,
Thank you.
Balvinder, Vivek ji, and so many. 9 faculty were there from VJTI Mumbai. That's great. So it kind of full-fledged event. Now,
So
first
that
of
gives a pleasure. If somebody is really listening, then that is a true examination.